Okay, here's the video presentation of section 4.6, functions of two variables. And our objective will be to graph functions of two variables in a two-dimensional coordinate system and to read such graphs. Okay, so what this means is we're going to get functions that have two independent variables. And then we will get a value for one of the independent variables so that we can graph it on a two-dimensional plane. Because with three variables, that's not two dimensions, that's three dimensions. So it's kind of cool stuff, and it leads to everything we're going to do in 4.7 in just a little bit. Okay, let's start with this. Everybody, a rectangle. All right, now you know that rectangles have two key dimensions. They have a length and they have a width. All right, and then in pre-algebra, even way back in the day, you guys did stuff like, what is the perimeter of this rectangle right here? And you had a formula. You didn't know it then, but that formula was actually a formula of two variables. And the appropriate function notation for a formula of two variables is to go perimeter of, and this perimeter is going to be in terms of length and width. So you got L comma W instead of just like P of X. And what is the perimeter? Well, to get all the way around this rectangle, what do you have? Well, I have the length on the bottom, the length on the top, that'd be two lengths, plus, and then I have the width on the right and the same width on the left, that's 2W, and there's my function perimeter in terms of length and width, and that equals 2 times the length plus 2 times the width. Now, we're going to graph this function in two variables on a coordinate plane with just two dimensions. So we're going to start by doing curves of constant width. And what does that mean? Well, here, since I'm going to be given some values for the width of the rectangle, that means my only variable left will be length as an independent variable. So I'm going to put the length on the horizontal axis and the perimeter on the vertical axis. So this has to be an L right there. Now, keep this simple, you guys. Let's pick a very excuse me, a very simple width of that rectangle right there. Could I just say the width is 1? And if this width right here was a 1, wouldn't I just have the perimeter is 2 times L plus 2 times 1, or perimeter is 2L plus 2? And now let's graph this. But again, this is real world here. We're talking perimeter of this rectangle, so there's going to be a restricted domain. Think about that. Now, if I was just graphing P equals 2L plus 2, I would think, okay, my y-intercept is 2, and I'd put a dot right there. But I'm going to put an open dot right there because, all right, horizontally, this length right here cannot be 0. Open dot right there. And then from there, I'm going to do a slope of 2 up and 1 over, 2 up and 1 over, and I keep doing that and doing that. So that's just going to create a ray coming from that open dot on the y-axis, or in this case, the p-axis, with a slope of 2. And there's my curve of constant width for perimeter if the width is 1. Now, you notice that I have a comma right here too. That's because there's a restricted domain here. Obviously, if you look at this graph, what can my L's be? Well, they've got to be greater than L equals 0. So L greater than 0. All right? Now, let's do another curve of constant width because they did say curves, plural. So how about we just go W equals 2? Now the same thing happens, but now W is 2. So this is going to become a 4. So I have P equals 2L plus 4. And now the only thing that's going to change is my y-intercept instead of 2 is 4. And I need an open dot right there. My slope is still 2, so I'm going to have a ray parallel to my previous ray. And guess what? open dot. My L's are everything to the right, so I'm going to have the same restricted domain. L has to be greater than 0. One more. W equals 3. Okay, so now if this W is a 3, we have 2 times 3 is 6. So perimeter is going to be 2L plus 6. So now my open dot's going to go up to 6. And I'm still going to have a parallel ray with a slope of 2. There it is right there. All right, and look at what we have here now. Same restricted domain. These L's have to be greater than 0. So again, L is greater than 0. Now, those are 3 curves of constant width representing the perimeter of this rectangle right there. Really cool stuff. All right, it looks like they want us to do a little bit more with the perimeter of this rectangle. So what could they ask us for next? Let's see. Oh, yeah. How about if we graph on a 2-dimensional plane the curves of constant perimeter? Now, constant perimeter, that means my output P is given. All right, so that's going to change things up ever so slightly on the graph here. All right, and here's the situation. Okay, constant perimeter, that means they're going to give me a perimeter, and then I've got to take that number and set it equal to 2L plus 2W. So my variables are now length and width, and I've got to know which one's going to go on the horizontal axis. So perimeter is now constant, and it's the way they write the function notation for the 2 independent variables, L comma W. Think about a typical point, X comma Y. X is independent, Y depends on X. It's the same thing here. L is my independent variable, and W is my dependent variable. Putting L on the horizontal axis and W on the vertical axis. So we need W in terms of L to make that happen. Okay, I'll go and put that on the graph now. Okay, so I need a perimeter then to work with. So how about we say the perimeter is 4? Now you're going to have to do a little bit of algebra to graph this. So if this perimeter is 4, don't I have 4 equals 2L plus 2W? Why, yes. And because W is depending on L now, I've got to take this and I've got to solve for that W. You always solve for whatever is on your vertical axis. Okay, so what does W equal? Looks like we're going to skip a few steps. I hope you guys don't mind. Well, if I was solving for this W right here, the first thing I would do is subtract the 2 L's, so 4 minus 2L, and then I would divide by 2. Now let's clean this up so it's easy to graph. Well, 4 divided by 2 is 2, and negative 2L divided by 2 would be negative L, or minus L. And now look what I have. I have a segment again, with a y-intercept of 2 and a slope of negative 1. And you got to think about real domains here. So this y-intercept of 2, I'm going to go open dot right there. Because, all right, the length cannot be 0. I wouldn't have a rectangle if the length was 0. And then a slope of negative 1. So I'm going to do a segment going down with a slope of negative 1, just like that. And then, just like the length has to be greater than 0, the width also has to be greater than 0, so I better put an open dot right there. And by doing that perfect graph, I can clearly see my restricted domain right here. Here are all the L's that I can use right there. So 0 is less than L, and L is less than 2. And there is my first equation. W equals 2 minus L, where 0 is less than 1, or less than L, and L is less than 2. Let's write that together nice and neat. There you go. Now, they're going to give you another perimeter, and you will do the same thing. So, perimeter is now 8. So 8 has to equal 2L plus 2W. And again, just solve for the W. So W equals, well, the first thing you do is take that 8 and subtract the 2 L's. and then divide by 2. And let's write this nice so we can graph it real easily. 8 divided by 2 is 4. And again, negative 2L divided by 2 will give me a minus L. So now my y-intercept is 4. Open dot. My slope is still negative 1. So slope of negative 1, parallel to the previous segment. And going all the way down to the L axis, which is where W would be 0. So I need an open dot there too. And now once again, I can clearly see my restricted domain. I'm going from 0 to 4 exclusive. Or 0 is less than L and L is less than 4. Now let's put this together nice and neat. And there you go. And we're going to do one more. So perimeter is, well, let's see. I'm into patterns. So 4, 8. I bet you they're going to say P equals 12. Look at that. So now 12 equals 2L plus 2W. So solve for W. W equals that 12 minus the 2L's divided by that 2, which we would write as 12 divided by 2, 6, and then negative 2L divided by 2 minus L. And now the only thing that changes is my y-intercept goes to 6. An open dot at the 6, same slope of negative 1 until I get down to that L axis where W is 0 and W cannot be 0. Open dot right there. And now I see my restricted domain. This time I'm going to go from 0 to 1, 2, 3, 4, 5, 6. So 0 is less than L and L is less than 6. All right, put that all together nice and neat. And there are my curves of constant perimeter with not only the graphs, but the equations and the restricted domains. I kind of was so proud of this one, I put it together on one slide, nice and big, so we could look at it and go, oh, that's so cool. Right on. Okay, so this is the last example problem for 4.6, and this is a great problem. Okay, the volume of a cylinder is given by the formula. Now they've written this formula, volume in 2 variables, radius and height, and they actually gave it to you, but I'm trying to help you make sure you have this stuff memorized and you can recall it whenever. So we're talking a cylinder. Draw a picture of a cylinder. Now you guys know from geometry that the volume of any cylinder is always going to be the area of the base, which in this case is a perfect circle, times the height. So if the base is a circle, area of a circle is pi r squared times the height. And that's given in the problem. Volume of a cylinder in terms of radius and height is pi r squared times height. And then it says sketch the graphs of V versus R. You have not seen a lot of that notation right there in mathematics. But what does it mean? It's not difficult at all. V versus R, here's your 2 variables, and the variable on the left V depends on the variable on the right R. Every time it's written like that. So R is the independent variable and V is the dependent variable. V depends on R, V versus R. So that means they're going to have to give us some values for H so we can graph it. And look at here, for H equals 1, 2, and 3. So here's my graph right here. And again, V versus R, okay, R is on the horizontal axis and V will be on the vertical axis. All right, and now I get to choose some simple inputs R, so simple radii. What if I go like 0, 1, 2, and 3? Now I got to think about my outputs. So my outputs are going to be the radius square times pi when H equals 1. So I'm going to scale the V axis in terms of pi's. And I can think I can get away with every hash mark worth pi. Let's see. Yeah, there we go. 1 pi, 2, 3, 4, 5 pi, and so on. Perfect. All right. Now, let's just plot some points. So if H equals 1, well, let me write this down here, kind of organize things for you. H is 1. So now what I have here is this. Volume with a radius r and a height of 1 would be, well, if this h is 1, that's just pi r squared. Okay, now, if the radius, look at the graph, is 0, then my volume would be 0. And then I don't even have a cylinder, so I'm going to go an open dot right there. Now, if the radius is 1, 1 squared times pi, the volume is pi. Solid dot right there. If the radius is 2, 2 squared times pi, that'd be 4 pi. So let's put a dot up here at 4 pi. About right in there. Okay? And if the radius is 3, 3 squared is 9, 9 pi. The volume is 9 pi. So let's let 3 go up to 9 pi. About right there. Okay? And now let's draw a smooth curve through the scatter plot. And there's my curve of constant height h right there. V versus r. And there it is. Now, I'm not going to do the restricted domains because they're pretty obvious again right here. You guys all realize that the radius, for me to have a cylinder, my radius has to be greater than 0, which you're going to see in every graph. You're going to see an open dot right there, and then your curves. Okay, so now let's go ahead and do h equals 2. So v of r comma 2. All right, well, if h is 2, I have 2 pi r squared. Now, my first graph was v equals pi r squared. My second graph is v equals 2 pi r squared. So doesn't that mean I can really do this easily by just simpling my output at every r value? So if I double 0, I'm still at 0. If I double the output at 1, which is pi, I'd have 2 pi. And if I double this output, which was 4 pi, it's now going to be up here at 8 pi. And if I double this output, which was 9 pi, I'd be at 18 pi, which I don't have room for. So I'm just going to wing it like, there it is. And there's my curve. V of r comma 2 is 2 pi r squared, and I see that r has to be greater than 0 again. Let's do one more. H equals 3. So v of r comma 3. Well, now I have what? 3 pi r squared. And I'm going to graph it the same way. I'm just going to take my outputs at every r value of my original graph and triple them. So 0 is still 0, but that 1 pi is now a 3 pi. And this, what was that, a 4 pi is now a 12 pi. And I don't have room again to do any more, so I'm just going to have my curve come through just like this. And there is v of r comma 3, which equals 3 pi r squared. And obviously r is greater than 0. Isn't that cool? Okay, B. Sketch the graphs of h versus r. Remember what that means. H depends on r. And they're going to give you a volume, 36 pi. H depends on r. So let's do this perfectly and set up a little table right here. All right, H depends on r. So that means r would go up top, and then H would go down here. Note this simple r values right there. And H is right there. Okay, now, they gave me a volume of 36 pi. So I've got to plug that into my equation and solve for the dependent variable h. So volume equals pi r squared h. And we're going to substitute that 36 pi for my v. So 36 pi equals pi r squared h. All right, you divide both sides by pi, and you're left with 36 equals r squared h. And divide by r squared, and it looks to me like h equals 36 over r squared. And make sure I skip some steps there. You see that I just canceled the pi's because we divided by pi, and then we divided by the r squared. And now let's crunch some numbers. 36 over 1 squared, 36. 36 over 2 squared, that'd be 36 over 4, and that's 9. 36 over 3 squared, that'd be 36 over 9, which is 4. And then 36 over 4 squared, that's 36 over 16, which I punched out and got a 2.25. And then 36 over 25, I punched out, and I got a 1.44. And then I get to go 36 over 36. I'm not going to punch that one out. It's a 1. Okay? And let's draw the appropriate graph and plot those points. Okay, so here we go. Note my R's, 1, 2, 3, 4, and so on. And I'm scaling my H-axis by 3s. So let's plot the point 1, 36. Right about there. Okay, 2, 9. 2 and 9. 3, 4. Okay, that's going to be about what right in there. And then, you know, I know it's just going to get closer and closer and closer to the R axis. So I'm going to kind of wing it here, you guys. Just go a little bit lower and a little bit lower and a little bit lower. And I can keep going as long as I want. And then I'm going to put a smooth curve through the scatter plot. And that is my graph of H versus R given a volume of 36 pi right there. Love this stuff. Now, they want us to do the same thing with the 72 pi. Piece of cake. 72 pi. Now, I'm going to show every step, but you guys, honestly, here I was at 36 pi. So now I could just double every output and get my graph. And it's going to look very similar. In fact, I could just rescale my H-axis. But let's show every step just to make sure we got this down. Okay, so now my volume is 72 pi. So 72 pi has to equal pi r squared times H. And if I solve that for H, I cancel the pi's. And I see H equals 72 divided by the radius squared. Let's do our table. Okay, so 72 divided by 1 is 72. Oh, and look at here, I'm talking about what I mentioned a second ago. So I could crunch all these numbers, but again, because 72 pi is twice as much as 36 pi, I'm just doubling every output. Look at this, 36 times 2, 72. 9 times 2, 18. 4 times 2, 8. 2.25 times 2, 4.5. 1.44 times 2, 2.88. Boy, that's a lot easier than recrunching all these numbers. And 1 times 2 is 2. And now I'm going to use my exact graph and simply rescale my H-axis. And then I plot the points. 1, 72, 66. What's that? 72 right there. Okay. And then 2, 18. 2 and 18. 3 and 8. Right up in there. And then just get closer and closer and closer to the R-axis. Smooth curve through the scatter plot. And there is our graph of H versus R if our given volume is 72 pi. Oh, this is cool. Now, part C. If H is held constant, what happens to the volume when the radius is doubled? Well, think about that. If I double this R, so it becomes 2 times R, and I square that, aren't I actually going to get a volume that's 4 times the previous volume? Let me prove that to you. So now I'm going to double the R. So this R is now 2R, and the H is constant. Okay, there we go. So what would that do to my formula? Well, I've got pi, and now instead of r squared, I have 2r squared. And if I square that 2, I get a 4, so that would give me a 4. And then pi r squared h, 4 pi r squared h. And that's 4 times my original formula. 4 times v of r comma h. So what did we do to our volume? We multiplied it by 4, or we quadrupled it. V is quadrupled. All right, now the problems for this lesson would be 4.6, which is on page 154, 1 through 6. Have some fun.